All right, let's get down to actually computing some limits now, algebraically. So let's start with this one here. It's a little scrunched up here. Yep. So let's compute the limit as x approaches 3 of x minus 2 over x squared minus 4. If we think back to those limit laws and what it means to be continuous, x equals 3, the bottom's not 0, so this function's continuous at x equals 3, and therefore we just plug it in. We get 3 minus 2 over 9 minus 4, and that simplifies to 1/5. But what happens if instead I ask the question, well, what's the limit as x approaches 2 of this thing? Well, x equals 2 is no longer in the domain of this function, right? Because if I plug it into the bottom, I'm going to get 0, and this function's undefined. But what we can do is, using properties of limits, we know we can, factor this out, cancel stuff, and the limit won't change when we do that. So let's take this function here, and we're going to factor the bottom. And then look what happens. We can cancel the x minus 2's, and this turns out to just be the limit as x approaches 2 of 1 over x plus 2, which is 1/4. So this is one of the many tricks we can use to actually evaluate a limit. Right? There's sort of 4 common themes that'll show up in the limits we'll discuss here. And one of the 4 is, well, you might have to, if you wind up with 0 over 0, which is what we get in this case, right? If I try to just plug in 2 directly, I get 0 over 0. Whenever you see that 0 over 0 is when one of these 4 techniques will usually help you out. It's not guaranteed, but this is usually the approach you're going to want to take. Right, so again, the first part here is, well, we can factor and cancel. And hopefully the thing that causes the 0 on top will cancel with the thing that causes the 0 on the bottom. All right, well, what else can happen? That's sort of one method. Another method that comes up is we might need to do some expansion and combination and reorganizing. So what is that? What do I mean here? So another example, let's say we look at the limit as h approaches 2 of as h approaches 0 of h plus 2 squared minus h squared, 2 squared, 4, over h. Right, let's say we're looking at a limit like this. Okay. Sorry, I was thinking through that example in my head as I was writing it. Yeah, so we're going to look at the limit as h approaches 0 of h plus 2 squared minus 4 all over h. So as it stands, if we plug h into the bottom, we get 0. If we plug h into the top, we're going to get 4 minus 4, which is also 0. So maybe there's something we can do. So let's start by multiplying out this stuff on the top. H squared plus 4h plus 4 minus 4 all over h. So look, this plus 4 and this minus 4 cancel. And let's look at what we have left. Can we simplify this at all? We can, right? This h will cancel this and the square up here. And we'll be left with limit as h goes to 0 of h plus 4. And look, now we can just plug in the 0 and we get 4. So again, whenever you have this 0 over 0 show up in a limit, there's hope that we can do it. Now, if it's something like 5 over 0 or any other number over 0, then the limit's probably undefined, right? Think of something like the limit is x goes to 1 of 1 over x minus 1, right? And when it's undefined, you usually have some kind of like a vertical asymptote, right? Or somewhere where the function can't be drawn. All right. Let's look at another example, another way things could come up. Let's do the limit. Let's again say this time, I don't know, r goes to 0. And let's do square root of 9 plus r minus 3 all over r. Right. Let's check this out. So again, if we plug in 0 to the top, we're going to get square root of 9, which is 3, minus 3. So 0 on the top. We plug in r equals 0 on the bottom, we get another 0. So we have another instance of this 0 over 0 trend. So what can we do here? There's no factoring or combining or simplifying that's really going to help us out this time. But there is a technique that'll help us. It's called rationalization. Right? What we do for that is we say, well, look at this thing up here. We're going to take the part that has the square root in it. Right, or the top here, it should be like two different parts, either a plus or a minus on top, it doesn't matter. And we're going to switch it to a plus. Plus r, 3. And again, whenever we want to multiply by something, we have to sort of make sure we're multiplying by 1. So we have to put this over the same thing. Right? Now, if we multiply this out, let's see what happens. Right? So let's multiply this out the long way. So the first times the first. So that's actually 2 copies of the same thing. Right? Then we get the outsides, so 3 square root of 9 plus r, plus 3 square root of 9 plus r, and then negative 3 times positive 3 is minus 9. Right? And on the bottom here, the bottom I would recommend just sort of leaving as is. There's not going to be much we can really do about it. Okay. So now let's look what happens. This and this are going to cancel each other out because they're just the same thing but opposite signs. This square here cancels that square root. And so what do we get left over? Well, we have limit as r goes to 0 of 9 plus r minus 9 over r times square root of 9 plus r plus 3. Now we still have some more simplification to go, but you can see here that, well, something's happening, right? So let's keep simplifying, because if we don't keep simplifying, if we plug in r equals 0, we're still going to have 0 over 0. So we've not fixed the problem just yet. But here we can cancel these 9s. Right, so this is limit as r goes to 0, r over r times square root of 9 plus r plus 3. And now look, this r cancels with this one and leaves a 1 on top. Now let me go down to the next line. Right. The limit as r goes to 0. This is now 1 over square root of 9 plus r plus 3. So when we plug in r equals 0, we get 1 over square root of 9 plus 3. And I'll let you double check that this is 1/6. Right? Yeah, so this is one of the pretty useful techniques for computing these limits. Right? This is one that we call rationalization. I think I spelled that right. All right. So the last sort of thing that tends to come up in these type of limits here, when you get the 0 over 0. Sometimes this shows up because of rational functions. So let's say we were looking at an example like limit as, let's say as x goes to 4 of 1 over x minus 1 over 4 over x minus 4. Right, let's say we had something like this. Okay. So if you have a situation like this, what you want to do is get your numerator to have a common denominator. Right? You want to bring everything together, and that'll help you sort out any problems. So keep in mind here, this is the numerator is a fraction, and this whole thing's like a double fraction. Right? So we want to combine these. So over here, we have to multiply by 4 over 4 to give a common denominator. Over here, x over x. Right? So let's write out what happens there. Over here, we have 4 over 4x minus x over 4x. All of this is still over x minus 4. Okay. Let's combine the top into one fraction now. This is 4 minus x over 4x. And all that's divided by x minus 4. Now we really need to do some simplification. So remember, when we are dividing two fractions, maybe I'll do it right here, a little reminder. If we have a over b, make that look like a over b divided by c over d, you take the top fraction and you multiply it by the reciprocal of the bottom. Well, here the bottom is just x minus 4, but you can think of that as x minus 4 over 1. And so, here we have limit x goes to 4 of 4 minus x over 4x times 1 over x minus 4. Can we do any simplification here? Well, we can. You might want to do a little bit of adjustment first if you don't see it. There's a cancellation you can do right away here, and if you see it, by all means do it. But if you can't see it, this 4 minus x and this x minus 4 have some cancellation, because we can factor out a negative sign here. And hopefully you can see the cancellation. We have limit x goes to 4 of negative 1 over 4x. And so our final answer is minus 1 over 16. Right? So these are the 4 styles of limits that will tend to show up when you're doing this analytic computation. Or I guess I should say 5 styles, right? Either you can plug the number in because it's continuous and everything's fine, or you get something like 0 over 0, which is where one of these 4 techniques we talked about here come up. And then, again, one more time, if you wind up with something like any number that's not 0 divided by 0, for example, 5 over 0, well, then your limit's probably undefined. Right? And that's it for now.